Fluid mechanics has long relied on heavy, expensive equipment. We wanted to change that by bringing the power of the lab to the palm of our hand. Introducing the Arduino-based Smart Water Level Monitor. We built this with 3 goals: accessibility through low-cost hardware, insight into a real-time relationship between depth and pressure, and precision that prove digital sensor can outperform manual measurement. To show you the hardware making this possible, here is Liang Xijing.
Our prototype relies on 3 main hardware components. First, the Arduino Uno R3. This microcontroller acts as the central processing unit for the system. We paired it with a solderless breadboard, which allows us to easily distribute power and modify connection if needed. Next is the HCSR04 ultrasonic sensor. It operates at 40,000 Hz to measure the water depth by calculating the time of flight of sound pulses. Finally, we integrated a 0.96-inch OLED display. This output device is essential for visualizing our data and displaying the real-time pressure calculation. Now, let's move on to our assembly process.
Let's assemble the fluid monitor. Firstly, for the power rail, we use metal jumper wire to connect the Arduino 5V pin to the red rails and GND pin to the blue rails on the breadboard. As a result, the power rails can supply electricity from Arduino to the ultrasonic sensor and all LED display. Let's connect our HCSR04 ultrasonic sensor. This is the eyes of our project. We are using metal jumper wire to connect it VCC pin to the red rails and GND pin to the blue rails. Let's connect the drip pin to the Arduino pin 9 and the echo pin to the Arduino pin 10. This pin will help us send and receive the sound pulses to measure distance.
Now, we set up our 0.96-inch OLED display so we can see the water level readings in real time. Connect VCC pins and GND pins to the power rail, then connect the SCL pin to analog pin A5 and the SDA pin to analog pin A4 on Arduino. On the Arduino Uno, these 2 specific pins handle all our display data. Finally, the code. Plug the Arduino into your computer and open the Arduino IDE. Write our code and upload to our Arduino. When finished, the screen will flash and show system ready. This means our prototype is done and ready.
First, we ensured the container was dry and the Arduino system was reset. After marking manual reference heights, we poured water in 2 cm increments. We paused for 15 seconds between pours to let surface ripples settle. At each interval, up to 14 cm, we recorded the digital height and hydrostatic pressure from the OLED display to analyze the relationship between pressure and depth.
So, for our result, this is our complete dataset obtained from the prototype. We also calculate the theoretical pressure with our manual measure height using the formula P equals to rho GH. We compare the theoretical pressure and the experimental pressure. We came up with the all accuracy for each reading. For example, the manual height is 10 cm while the sensor height is 9.92 cm. And we calculate the percentage error is only 0.8%, which is very precise. Other than that, we also draw a graph that shows the relationship between the hydrostatic pressure and the water height. In the graph, we also visualize the comparison between theoretical pressure with experimental pressure. It shows a very perfect best fit line, which explains our sensor data is close enough to the theoretical result. In conclusion, our project successfully transformed fluid mechanics theory into a functional, low-cost prototype for real-time water level monitoring using Arduino instrumentation. By validating the hydrostatic pressure formula, our system achieved over 97% accuracy with an average error of only 1.0%.
This proves that digital sensors can effectively replace manual monitoring in industries like agriculture and water treatment. While we identified future upgrades like IoT integration, we have successfully bridged the gap between classroom physics and real-world engineering. That concludes our presentation. Thank you for your time.